Okay folks, so we're looking at lab 7 now. I had already recorded some of this 15-minute boring story, but I have a lot of it done already. Okay, but obviously I'll slow down and go through it with you to get you started. So we've got temperature in a plate, and what we're doing is we're chopping up the plate into loads into a square grid, and then we're using this formula here, and the formula in this form is probably the best one. Now what you need to understand is that so I and j are not exactly coordinates, they're like number of grid points over. So for example, T00 usually might be the bottom left of the plate, and then as you go over 1 you'd have T10, that'd be 1 over. Okay, maybe I'll show what I've done already. So we see this. So if you look at now this one is very unfortunate because the coordinates are actually equal to the things, but just for the moment assume that the distances the width of the squares aren't 1. Now they will be 1, but assume they aren't. So like T11 or T11 means 1 across in the x and 1 up in the y. And so along the bottom, it would be T00, T10, T20, T30, etc. Okay, and what that means is that this is the temperature at a point, and this is an average of 4 adjacent points. So the I-1 means the previous in the sense of x, I+1 means the next point in the sense of x, j-1 means the previous in the with respect to y, and j+1 means the next with respect to y. So really what this means is to the point left, right, bottom, top. So the 4 temperatures around it in the grid averaged out. Okay, so that's derived in the lectures, and we can do Jacobi method or Gauss-Seidel. Now, the Gauss-Seidel method is more accurate and it's easier to implement, which is funny. The Jacobi method is a little bit interesting in the sense that in the Gauss-Seidel method, the iterations, so we're going to be iterating towards a steady state solution, and in Gauss-Seidel, the intermediate calculations don't have any meaning, but for the Jacobi method, they actually do, and we might get to that a little bit later on. So the first bit by hand on paper, draw the square plate in XY plane. So here we've done a 3x3 square plate bounded by these lines. Now it doesn't say it, but we're going to do it with 4 internal grid points. So that's what's done here. Now there's a small typo in this. This should be 3 minus x. I'll have to get onto you about that quickly. And so if you calculate now, where's the line y equal to 3? Well, that's up the top. So the temperature up the top is constant minus 90. X equal to 0 and x equal to 3 is the left and the right. So the temperatures are minus 30 times the y coordinate. So at y equal to 1, you get minus 30. At y equal to 2, you get minus 60. And for the other formula, if you do 3 minus x, so that's y equal to 0, that's along the bottom. You've got x equal to 1 and x equal to 2, and they both give you 480. Now it's not great here. I've got a symmetry in the temperatures, but look, so be it. Okay. So we've done that for each of the 4 points. Write down an equation. Now I've done that here like this. So for each of the 4 points, I write down that the temperature at that point is to be the average of the 4 around it. And I also decided on initial temperatures. So for the initial temperatures, what I did was I said that I would choose the average of the known adjacent temperatures. So for example, for T11 is beside minus 30 and 480, and I took the average of those as 225, and I did that for all. Right, so we're going to go into VBA with this. So I just set it up here. What we're going to have, now you can be a bit creative here about like printing to a plate, but because we're doing Gauss-Seidel initially, the intermediate temperatures don't mean anything. So there's not really much point printing them. But there's lots of scope for play here, as we'll see. I'll probably send you YouTube to kind of give you an idea of how far you can push it. Okay. Okay, so into VBA. So usual crack, we have our variables. So the variables are the 4 temperatures and the row number. That's all we have. We give them initial values. The row number is equal to 2 and the temperatures as described there. We do a loop. Now, one of the things with the temperatures is you can actually pick any initial temperature. It doesn't matter. If you want to just pick 0, that's fine. And for example, if you're doing the Jacobi method, where the intermediate calculations make sense, if you start the temperature at 0, that's like the plate heating up from a temperature of 0. So that's interesting. So we do our printing, calculate the next values of the temperatures in the rows. Jacobi is using all the old values and Gauss-Seidel will use the latest. That's what we'll do. And then the stopping rule, it's mentioned the page, so you keep on going until the difference between the temperature and the previous temperature is less than this times the current temperature. And you must do it for all of the 4 temperatures. So I'll let you think about that. And so that's how you start that one. Now, then we're looking at arrays. So now I have it written here. I don't think I'm going to, I think it's important that you can use arrays. I mean, programming is very important for, you know, probably in your career. And really I should have done more with arrays. And I think I intended on doing arrays this year, but with the COVID, like I'm trying to be kind of friendly to you. So some people struggle a little bit with arrays, but those of you who can do it, I'd like you to do it. But I will not force you into doing it in an assessment. Okay, but we'll forget about that. We'll think of the learning. So now we're going to do a 5 by 5. See, the thing is, with a 5 by 5, you have 16 variables. You do not want to be writing down the formulas for all of them. So here's my 5 by 5 grid. And I can, okay, I've labeled the rows. So I'll just show you what I mean there. Now here it's saying rows. You can do rows or columns. Now it might change things later on. It's difficult now. I'm saying rows there. To me, it doesn't really matter. You see, is the point. So you've got options. You can do so. One, you can do it like Excel. So the I would be the rows and the J would be the columns, and that's fine. That's possibly the easier thing to do. Or you can do it the alternative way, and then the printing gets harder. But we'll do it the alternative way. So, what am I thinking here? What I'm going to think of is all of the temperatures. I'm going to, at all the internal grid points, I'm going to want to plot them. So what I'm going to do is I'm going to make the indices to be like the Excel worksheet. So I got I equal to 1, I equal to 2. Now if that's saying 0 to 5, I'm saying not to do that. I equal to 3, I equal to 4, I equal to 5, I equal to 6. And they're like the rows in an Excel sheet. So you can do it what I described previously. It doesn't really matter. And then J equal to 1, J equal to 2, J equal to 3, J equal to 4, J equal to 5, J equal to 6. Okay. So something like that. So that's that. Take a general point and write down the formula in terms of adjacent. So that's the formula that we saw previously. And then suppose the boundary temperature is given like this. Calculate the boundary temperatures. Well, it's just done. For each of the 4 internal grid points, write down an equation. Well, that's obviously, that's contradictory. So I'm going to improve instructions there. And decide on initial temperatures. Now, 30 is a good shout as an initial temperature because it's the average of all the known temperatures. But actually, I'm going to run with 0 and do Jacobi method. I'll show you something a bit cooler. So, let's see how we go. So, right. Okay. Let's do it. So we'll give you an idea of what you have to do. So as usual, you need to define variables but here also and an array. Now I'll do the array for us here. Dim dblt, and we want to do int I. Well, we can use rows and columns. Int row, int column, as double, as array, is it? I'll have to be careful here. Yeah, I've forgotten the thing. Oh yeah, it works like this. Oh yeah, we can just do 0 to 5. Okay, apologies. A bit rusty on this stuff myself. Now we're actually doing 1 to 6. 1 to 6 as double. And it actually knows that it's an array once we have this. Okay. Now we're also we are we going to have a row? Now we're not, so we need a new counter. So dim int c as integer. Okay, now thinking about the initial value, so what we have to do is we have to do the following. We have to set up all the boundary temperatures. So I'll do a little bit of that for you. So say the top temperatures are 0. So set top temperatures equal to 0. So this you do a for loop. So for int j, which corresponds to a column, equal to 1 to 6. I want to populate. Now, if you look at my thing, now you might have a different indexing. That's fine. So you might have done it differently, but I want to go with across row 1, across these j's, and set them all equal to 0. So it'll be dbl temperature. Now I'm going to want an old temperature here a bit later on if I'm doing Jacobi method. Okay, so this is row 1, and then across the columns equal to 0. Next int j. So yeah, in terms of variables, I'm also going to want the old one. Dim dblt old 1 to 6. Now I don't need to include the boundaries as old temperatures because they're not going to change. So I could just do 2 to 5, 2 to 5 as double. Okay. Okay, so that's the top temperatures. Now I want to do similar. Do similar for sides and bottom. Now, how will you do populate the internal temperatures all equal to, I'm going to go with 0 here. So you do for int j equal to 2 to 5 because you're just working on the internals. And then you make, if you're summing over a two-dimensional, you do a nested for. So another int I equal to 2 to 5 and put dbl t int I int j equal to 0. Next int I, next int j. Okay, so that's setting, and then int counter, we can probably start equal to 1. Okay, so now in our loop, we want to do printing, okay? And what you want to do here is do a big for loop. So in your printing, print in a big for loop all of the temperatures. Now you only really have to plot the boundary temperatures once, but it might just be as easy for keep plotting them. All of the temperatures in the array from I and j equal to 1 to 6. So you're going to print all of them. Then you're going to calculate the next. Now if you're doing the Gauss-Seidel method, it's actually easier. So for Gauss-Seidel, do a big for loop in a similar fashion, but only the temperatures in the interior change. for I and j equal to 2 to 5. And use this formula here. This formula here, wherever it is. Yeah. Okay. Now what I'm going to do is the Jacobi method. For Jacobi, need to use very latest values. Sorry, use old values. So for the Jacobi method, what you should do is before you calculate the new, before calculating the new values of t, record the old values by doing dBl t old equal to dBl t over all the indices 1 to 6. Okay, so then when you're writing down this thing, you're going to, all of these temperatures are going to be the old ones. So do similar to Gauss-Seidel, but use T in terms of T old. Okay, you're going to want to put up your counter, and then the stopping rule is going to be difficult to implement stopping rule. Maybe start with until C is bigger than 100, but then try and improve. So the problem with the stopping rule, which is the proper stopping rule, is the absolute value of T minus T old is less than 0.005 times the absolute value of T, but it has to be satisfied for all internal grid points. So you'll need to do some problem solving there. Okay, so I think that's enough to set you up, and I'm going to go off and finish this off.